Samudravasane Devi Parvatasthanamandale Vishnupatnyai Namastubhyam Padasparsham Kshamasvami. Those who dare to fly don't care to leave their footprints behind. Welcome to FVS. Good morning to all of you. Can you hear me and see my slide?
Yes, sir.
Thank you, Akshay. So we'll continue with the lecture number 21, in which we will just wind up on the load factor that we were discussing in the previous class and how it is related to the velocity through the flight envelope. And once we are done with that, we will, for most part of today's class, be talking about load transfer, how the load gets transferred predominantly from the, we're talking about the air loads over here, but it could be the other concentrated loads as well. How they get transferred from one component of the semi-monocoque structure to the other. That path is very important, and so we will look at how that is accomplished. And if time permits, we will do a little bit of revisiting of the materials from the new perspectives that we have gained from all of these lectures that we have had on the loads and load factor, the flight envelope, as well as the load transfer path. Based on that, we will look at the materials afresh. So you might recollect that we were looking at the load factor, and we said that there are basically two main considerations. One is the structural consideration, the other is the aerodynamic consideration. The aerodynamic consideration comes from the stall that we experience. That's basically this curve when the aircraft is flying in the right direction, that is basically with the top of the fuselage in the top and the bottom in the bottom. Or if it is gone through some kind of a maneuver and it's flying in an inverted way, then we need to consider the negative stall as well, and because of which we look at the minus CL max. And usually since we are not looking at symmetric airfoils, and even if we look at symmetric airfoils, what we are looking at is the lift coefficient of the aircraft as a whole over here, corresponding to its zero lift line, and there would not be symmetry about that. So in other words, if we were to plot CL versus alpha, so typically you would have a curve something like this, with a smaller CL max on the negative side compared to the positive side. So to account for that, we have another curve over here, which is OF, that we discussed in the previous class. So this OA and OF are coming from the aerodynamics, whereas the rest of the curves are predominantly coming from the structural limitations. In the structural limitations, as we discussed in the last class, are included the maximum load factor that it can encounter, and also the maximum dynamic pressure that it can encounter. The maximum load factor again has a positive and negative aspect to it. So the positive aspect is seen over here, that it cannot go beyond that. And when we say structural limitation, we also include the human limitation and also the limitation of the avionics that is involved, so that the avionics performs well within those load factors, because those load factors are eventually going to cause inertial loads, and that those inertial loads should be within the sustainability limit of humans, avionics, and the structure. And as far as that positive value is concerned, so that AC is basically given by your N1 over here, which is the limit load in the positive direction, and that value of N1 you can see is defined here. These are for civilian aircraft. For military aircraft, especially fighters, it would be a little higher compared to this, not little, probably quite higher even compared to the aerobatics. So as far as the normal aircraft are concerned, typically it's in the range of 2 to 3, whereas for semi-acrobatic aircraft, which need to perform a lot of maneuvers, it's about 4.5. And then if you look at aerobatic aircraft, it's about 6. On the other hand, for fighters, you would have typically of the order of 8 or so, sometimes a little more than that as well.
Sir, excuse me, sir.
Yeah.
Sir, can we just zoom in the screen, please?
Yeah, sure. Are you able to see it better now?
Yeah, that's fine, sir. Thanks.
Okay, yeah. So the N1 values are typically in the range of 2 to 3 for normal aircraft, 6 for acrobatic aircraft, about 8 for fighter aircraft. And then if we look at, let us say, the other limit that we have, which is on the negative side, which is typically half of that of the positive side. So this FE is determined by the load factor N3 that you see over here, and that's what you see in the last row of this table. And N3 is about 1 for the normal aircraft, about 1.8 for the semi-acrobatic, and up to 3 for the aerobatic kind of aircraft. So it would be in the range of around 4 for typically half of the N1 in the negative direction for fighter aircraft. And in between, we also have, we were saying that as far as the dive speed is concerned, we don't have as strict a limitation on the load factor for the structural design as for the design cruising speed. So at the design cruising speed that you see over here, you have a certain value of the N maximum that is to be allowed for in the structural design, that is N1 in the positive direction and N3 in the negative direction. But at the design diving speed, which is like a never exceed speed, you're not supposed to exceed that, you would end up with a disastrous structural failure as bad as the wing breaking off the fuselage. So and therefore you lose your all your lift, and therefore because of the loss of the lift, the aircraft will eventually crash. So at that design diving speed, the maximum N that or load factor that we need to design for is N2, which is much smaller compared to the N1 that was there in the positive direction. And you may not even need to design it in the negative direction, because inverted flight at such a high speed may not be performed unless it's a very strange situation. So yes.
Why this negative load factor is less as compared to the positive load
factor? So because you rarely fly in that situation, so it is not a very common situation. So you would get into that kind of a situation typically when the aircraft is in an inverted position. So you're basically, what you're saying is that the lift and the weight are acting in the same direction. So in other words, the lift is in the same direction as the weight. So that kind of flight configuration in which the aircraft flies is very unusual. So the certifying authorities, whether it is FAA or MIL, or ESA, or in India you have the CEMILAC or the DGCA, they prescribe certain limits for these aircraft based on what are their typical missions for each type of aircraft, and therefore what is the range that they might encounter. So already there is a level of, there's a factor built into this. And over and above this, as I said, we are going to bring in the factor of 1.25 as far as the deflections are concerned, and about 1.5 as far as the failure, which is strength, is concerned. So for a strength-based design and a stiffness-based design. So that is the reason why on the negative side, because you do not you very rarely fly in that situation. It could be probably to overcome something, or even in an acrobatic aircraft, which typically performs that, 3 is more than sufficient, and for a fighter aircraft about 4 is sufficient. So that is the reason why the limitations are much lesser over there. The other thing is, from a human perspective also, if you see what the positive load factor basically means is that as long as it is greater than 1, you feel heavier than you usually are, and basically there's a lesser blood supply to the brain. On the other hand, the negative means that there is even more blood supply to the brain than usual, and that could cause brain hemorrhage. Basically, the blood vessels which are going towards the brain can rupture, and it could be much more disastrous. So the ability of a human being to bear negative G loads is also little lesser compared to bearing the positive G loads, even if they are well trained, either to be a fighter pilot or even an astronaut for that matter. So is that clear?
But from a structure perspective, it can take like both negative.
Yeah, absolutely. Yeah, you're right. That from a purely structural point of view, it could probably take that kind of a load. So, but what we are basically saying is that when we are designing this, because under that situation, the lift and the weight, remember, are acting in the same direction. So the weight is adding up to the lift in terms of that. So you have an additional G coming out of that. So for example, when we say n equal to 1 is the cruise flight, what we are saying is the lift is equal to the weight, but actually remember that the aircraft, when it is cruising, it's actually not accelerating at all. It is actually going at a constant speed, cruise speed. So n equal to 1 is actually a zero acceleration flight as far as an Earth fixed reference frame is concerned. So in that sense, if you look at it from that perspective, truly speaking, your actual x-axis should have been over here. So that kind of adds another n equal to 1 factor over there. So it's not as different as it seems between the negative limit and the positive limit. Is that clear?
Yes, sir.
Okay. So coming back, we were talking about the limits, and so as far as the design diving speed is concerned, the requirement is a little less stringent from a design perspective, and your n factor that you designed for is of the order of 3/4 of the maximum at the designed cruise speed. So at the design dive speed, you need to design only for about 3/4 of the design, what you are designing it for the design cruise speed. And similarly, you would see that it's approximately of that 3/4 order that you see for the semi-acrobatic and the aerobatic aircraft as well. So this fighter aircraft would typically be of the order of 6. Again, there's a lot of variation from one fighter to another. For example, some of the Sukhois have much larger than this. They could go as high as 12 from purely structural point of view. But again, whether the pilot is able to handle that is always a question. So when you say the aircraft is capable of that, it is basically means that the structure and the avionics are capable of handling that, but the pilot may or may not be able to handle that. So these are the things that are important. The other important thing is where you design the structure for. So what we were saying is that anything above VD, what happens is that the Q or the dynamic pressure becomes very large, and because of that the loads are going to be very large. So the Q max is going to be the dictating factor beyond velocities VD. So in other words, for all velocities which are greater than VD, you have the problem because of very large dynamic pressure. Whereas anything above load factor corresponding to N1 is basically a situation where the inertial loads are going to be very large. large, whereas dynamic pressure basically means that the aerodynamic loads are going to be very large, and what we mean by the load factor is that the inertial loads are going to be very large. So this point C that I've circled here becomes a critical point over there, because at that particular point you're actually seeing that there is a possibility of the both the speed being large, much larger than the maneuver speed that you have, which is VA, which is the maximum maneuver speed. So you, if at all you would want to do maneuvers of high load factors, you try to do it in that region, so that if at all there is a danger, it's only a stall, and from which you can much more easily recover than getting into a structural kind of a distortion where the wing bends into a plastic regime and therefore has some permanent deformation, which is what will happen at velocities greater than VA. So most maneuvers are performed in the speeds which are less than VA, which is why VA is called as the maneuver speed, by which what we actually mean is the maximum maneuver speed. Though typically it is just claimed to be the maneuver speed, what we mean is you should not attempt to perform maneuvers beyond that, unless let's say you have a very experienced pilot and or some emergency situation, and or the weather is very clear, these kinds of things, because we have not yet talked about the effect of the weather, in particular gust, so we'll come to that shortly. So coming back, so this point C as well as the point D1 become very critical points from a structural designer's point of view. We would like to ensure that under those conditions of N1 comma VC, that is what this point C is actually. You can see that the Y coordinate is N1 and the X coordinate is VC over there, whereas for the point D1, sorry, it's the other way around, the X and Y. So the velocity is Vd, and the speed that you have or the load factor is N2, right? So this becomes a critical kind of a situation. In addition, you have to always check for the point E, which is once again going to be given by the same speed Vc, but the load factor is going to be minus N3. This usually is not a very critical thing from a structural design point of view. If you have designed it for VC, N1 and VD, N2, in most situations you will see that VC, minus N3 is usually taken care of by automatically. But nonetheless, you do need to check, especially if you have a unique kind of a design, let's say a flying wing or some new kind of configurations which have not been hitherto tried out commonly. So in such situations, you might want to actually check for that to see no particular component is actually suffering a very large load or deformation. It's well within the limits. So that's basically what is the takeaway from this for us. The other thing which I haven't yet mentioned is basically your gust. There's a possibility of gusts, and gusts are basically winds which are in the vertical direction. Either it could be an up gust or a down gust, both of which have the possibility of changing the angle of attack. I'm sure you'd have come across this in your aerodynamics and flight mechanics classes. So basically what is happening is you have an aircraft that is there, and that is flying at a particular velocity. So this is the free flow velocity at a far away distance. So if you have, let's say, the zero lift line of the aircraft, whatever angle that zero lift line of the aircraft, not of the wing alone, that is making with the velocity direction is your angle of attack. But you see that once there is a gust, let's say for example there is an upward gust, so you have this V infinity, and then you have an upward gust as well, which is, let's say, having a velocity u, usually much lesser than V infinity. But what that basically means is that you're going to have the resultant velocity vector along this dotted line. So this is the resultant velocity vector, let's say VR, So this resultant velocity vector now with respect to the zero lift line of the aircraft is going to make an angle which was the original angle, let's say alpha naught, plus a delta alpha, which is going to come from this additional angle basically created by the upward gust. So this is the speed of the upward gust. On the other hand, a downward gust will have the tendency to reduce the angle of attack. So essentially what's going to happen is that at n equal to 1, you typically will draw a straight line because what happens is because of the fact that this delta alpha is relatively small angle, you can say delta alpha is approximately equal to your u divided by v infinity. And so that being the case, you know that the speed is v infinity, and the lift is going to be given by your dynamic speed, which is dynamic pressure, which is half rho v squared into your s, which is the reference area, which is the wing area typically, into your CL, which can be broken up into let's say a CL naught plus a CL alpha into the angle of attack, the total angle of attack that you have. Now if you're defining the angle of attacks with respect to the zero lift line of the aircraft, then what you're basically doing in this CL curve is shifting your y-axis to here, so that with respect to this is the CL with respect to a zero lift line, whereas this could be with respect to some other reference line that you have on the aircraft, which you're defining as the x-axis. So once you do that, your CL naught will be taken care of automatically in that, and so essentially you have a CL alpha into alpha. So when you're talking about an L by W, you're basically dividing this by W, and your angle of attack now, this alpha, is going to be equal to your original alpha naught plus your delta alpha, which we have shown for very small angles to be u by v or v infinity. So that being the case, so what happens is this v cancels with this v squared over here. So you basically are having that delta L that you are talking about over there. That is the change in angle that you're talking about, change in the lift because of the change in the angle of attack. So in other words, we already have an L naught because of this, and then so we are subtracting that L naught from the total lift. So you get what is known as your delta L, or the change in lift because of the upward gust. And that change in lift, or rather an increase in lift because it's an upward gust, is going to be linear in your V. So in other words, you're going to have a straight line, and which is why, let me just clear the pen markings over here. So now you see that what we are talking about is that your delta alpha, sorry, the delta L, and therefore delta n are both going to be proportional to the velocity. And typically for the different types of aircraft, just like N1, N2 and N3 are defined, you would have the value of n at the cruise speed and or the diving speed defined as well for the different types of aircraft. And so since we know that this is proportional to V, obviously on the NV curve, this is going to be a straight line. So that straight line is going to start at this particular point, that is basically at the speed 0. You're going to have, because that's the level and cruise flight where n equal to 1. And so at the cruise speed, a particular factor n is mentioned, just like n1, n2, n3 are mentioned. For the gusts also, these factors are mentioned at some value. I'm plotting this above the n1 value, but it may or may not be. it could vary in different cases. So it depends on the altitude as well, because at lower altitudes you typically have larger gust speeds, whereas as you go to higher altitudes you have much lesser gust speeds, and so you typically have a constant gust speed defined up to a particular altitude around 20,000 feet, and then from 20,000 feet to about 50,000 feet it reduces linearly, and beyond 50,000 feet you don't consider gusts as well at all. So this is not an issue at all. So it depends on the particular altitude, but as I said, in many situations you might be plotting this flight speed instead as an equivalent airspeed, that is by taking the square root of the ratio of the densities at that particular altitude and the sea level into account, so that what you're looking at is the dynamic pressure, eventually square roots. So because of that you might sometimes consider the same flight envelope for different altitudes, but it's not a good practice to have, because it's not only the density which varies with altitude, but the value of CL alpha, CL max sometimes could change, and some of the other aspects could change as well. So it's better to do it at certain altitudes, specific altitudes, to ensure that you are safe at all altitudes. So at that particular altitude at which this flight envelope is, and for that particular type of aircraft, there is a particular N4 that is defined over here, and we draw a straight line from this point to here, and similarly another point is defined in the negative direction for downward gusts. So you basically draw a straight line over there as well. Similarly, at the design diving speed also, there is another n value which is typically specified both on the positive and the negative sides, and you typically join that as well with straight lines from the point n equal to 1 and v equal to 0. Similarly, you draw another straight line to this point on the negative side as well. And then, so in between these speeds, that is between the design cruising speed and the design diving speed, there is a linear interpolation that happens. So in other words, geometrically it's equivalent to joining these 2 points. So now this becomes this is the maximum gust that you can experience at that particular altitude, and so therefore your structural design should be able to take care of this limit as well. So if you let me use a different color over here. So now what happens is that the flight envelope that you had now becomes, of course, below the stall speed it doesn't get affected at all. It is the same as before. But now once we go beyond the stall speed, what we are saying is that the real consideration that we should have is something like this. This is basically the outer portion of this curve, that is the real flight envelope. Now this becomes a little too complicated to have. So what people typically do is to go a little higher over there and take a straight line over there, and probably come through this and this, so that you are designing for a much larger Nmax than what the point C might tell you. Of course, I've drawn it in a little exaggerated fashion here as far as the gust is concerned. Usually the amount by which it pushes it out is not way too much from the values that we talked about 2.1 to 1 range that we were talking about. So for the normal aircraft, so it would probably shift it by a few decimal points here and there. So that's what typically it is, but that does need to be taken into consideration. And again, this way of taking straight lines and getting the new flight envelope is it's actually kind of an outdated antique technique which most large aircraft manufacturers no longer use, because they have some kind of a spectral density of the gusts that are observed, which have been recorded over a long period of time. So statistically they have a much better idea of what typical gust to experience in which different kinds of weathers, etc., and what is the worst kind of weather situation for the typical flight path of that aircraft in different seasons, and taking that worst case scenario, they come up with some kind of algorithm for that, and that more or less is a straight line, but the slope that you get would be slightly different from what you get from these tabulated values. But for a first cut preliminary analysis, this is good enough from what the certifying agencies typically specify. So once you take that into account, most probably you're taking into account the other aspects as well. So This is basically what is the takeaway for us from a structural perspective for this course. We have not gone deep into understanding how this flight envelope is developed, but we want to get the critical points, the maximum dynamic pressure and the maximum lift factors, both in the positive and the negative directions, which are modified for the up gusts and the down gusts that can typically result. So under that kind of a situation, we have the critical things that the critical kind of situation that the aircraft structural components have to be designed for. So with this, I'm concluding the discussion on the load factor, and we will move on to load transfer. But if there are any questions on this, I'll be happy to answer. Okay, so let's move on. Somebody had a question? Okay. So let's go on to load transfer. So as I said, this is basically because we are having a semi-monocoque construction, so many different components like the spars, within the spar cap, the spar web, and then the stringers, different kind of behavior for the top stringers and bottom stringers, some in compression, some in tension. Then you have the skin and the maybe if it's a stuffing like what we saw in the previous class of a foam in between for a sandwich kind of a construction, etc. And multiple boxes, some cases if you have multiple spars, and all of those kinds of situations are there. So all of these components, how they share the load, we have seen in a very qualitative sense earlier as well, but now that we have done a little more study of the various kinds of loads that occur, the typical characteristics of one-dimensional structures like beams, rods and rods or columns and shafts, and the 2D shear panels that the cover skin and the shear web are basically for the spar. So all of these, under all of these new light that we have, we would like to understand the load transfer from this better perspective that we have now, and under the severe conditions that those large values of n and or speeds can result in. So the wing and the fuselage are basically collection of the basic structural elements, because though you have the stabilizers, which is the vertical tail and the horizontal tail, their behavior is somewhat very similar to that of the wing. And similarly, your elevator and rudder behavior very similar to the flaps and or ailerons on the wing. So if we steady the wing, it's as good as having steadied the stabilizers as well. But of course, for the vertical stabilizer, we do need to take into consideration the fact that it's not having that symmetry that the horizontal tail and the wing have. So that can be a certain consideration to have. In addition, also, there's a very good question that one of the students asked. Unfortunately, I have not yet replied to that, but maybe I can take it up right now. So he had asked that when you have the engines on the aircraft wing, whether on top or bottom, you are going to have the thrust which is going to compensate for the drag and therefore reduce the bending loads because of the drag. So he was asking about podded aircraft, where you typically have the engines mounted not on the wing, but instead mounted on the fuselage. And if it's a civilian aircraft, you have multiple engines, and therefore it's if it's, let's say, a twin engine aircraft, those two engines are mounted on the rear end of the fuselage. In fact, I explained this in to some extent already. For business aircraft, you typically would have that kind of a situation where it is still accessible for maintenance, etc. So he was asking that once we have removed the engine from the wing and put it on the fuselage, the wing is not having a compensation for the drag bending because of the which it was having when the wing and the engine was on the wing. It's kind of very easy to answer that, because if you look at the dominant load is always the lift. You know that the lift to drag ratio is larger than 1. Depending upon the type of aircraft, it could be much larger than 1. And the more severe load is the lift compared to the drag. The other aspect is that from a bending perspective, what is important is the moment of inertia, and the moment of inertia in this direction is much lesser. That is where the lift is causing the bending. The moment of inertia of concern there is much lesser because the thickness is very small, whereas the chord is much larger than the thickness, because the thickness to chord ratio is typically of the order of 10%. So what happens is that the bending stiffness in this direction, that is in the drag direction, is much larger. So one, you have a lesser load by about 20%, and the second, you have a much larger moment of inertia. So if you, of course, it's an airfoil cross section, but just to get ballpark values, if you think of it as BH cube by 12 in one direction, where the B value is not the span, instead it is the chord. So CH cube by 12. On the other hand, you have, if you approximate it by a rectangular cross section, you have a C cube H by 12. So what you are essentially seeing is that if you look at the ratio of this, you are looking at a ratio of H by C squared. And so that's about H by C is of the order of 0.1. And so you have 0.1 squared or 0.01. And then further that L by D ratio comes in the denominator, so of the order of 4 or so. So you see that the bending moment and the bending stress that are going to come are much lesser. So it's not something very severe. So what the engine was doing over there in terms of a stress relief for the drag is that even that small amount it was further reducing. So not having the engine there is not going to be a very severe penalty in terms of the behavior to the drag. So that person who asked me this question on the email, are you satisfied with his answer, or do you have any other perspective to this?
Yes, sir.
Okay, thank you. So now, that's basically what it is. So let me just clear those pen markings. So, that's as far as the wing and fuselage are concerned. And typically when you have another thing while we are on that podded aircraft, so if you have the engine mounted on the fuselage, because you do not want the exhaust of that engine to affect the flow over the horizontal tail, you typically will have a horizontal tail which is more like a T-tail. So in other words, it will be on top of the vertical tail. The horizontal tail will not be at the bottom like what it is in this particular aircraft, but it will be on the top over here. And so there are certain considerations which are going to be a little more difficult over there, and the load on the vertical tail is also going to be much higher because it is going to transfer the load from the horizontal tail. So there are certain other complications that can arise when you're doing that. The other is, of course, in terms of the noise, the ability to withstand fire, etc., and how fast it transmits to the aircraft because it's much closer than the wing-mounted aircraft engine. So there are many design parameters, so we'll not go into all of that because most of them are beyond the structural perspective and will consume too much of time from this particular course. So I will stop that discussion for now. Now, so it's clear that instead of considering the tail, we can consider the wing for more structural aspects to have a qualitative understanding. Now, each component of the fuselage as well as the wing is going to be either a 2D structure, which is a shell or plate, or a panel, or it's going to be a 1D structure, which is going to be essentially the generalized beam that we are talking about, which includes shafts, rods, and columns. So axial and or torsion and or bending member, but usually there could be a combination of all of these. So the example, of course, is the box beam, a very crude example of which is shown on the top figure, both on the left as well as the right. And this box beam could be stringers at the maximum allowable distance from the neutral axis, because that's where you know that the bending loads are going to be very large, and therefore to increase the bending capability, you want to increase the bending stiffness EI, which means that for a chosen material E is fixed. So you want to increase the moment of inertia, and that moment of inertia is increased by having it as far away from the neutral axis as possible. So you have these stringers that you see over here. They are all as far as possible, both on the positive as well as the negative sides, from the neutral axis, which could be somewhere over here. So that's as far as the box beam is concerned. And in addition to the stringers, of course, it has the thin skin that you see over as the shear panel, and of course the spars as well. The thin skin includes the cover skin as well as the shear panels, which are coming because of the spars that you have over here. So essentially that whole thing is making up a box beam that you see, and that thin skin is what we looked at as the 2D member or the shear panel. And that's just like in the case of the stringers, to increase their bending contribution, you're trying to put them as far away from the neutral axis as possible. On the other hand, the thin skin, you're trying to ensure that it encloses as large a area as possible, because we saw that that area power 3/2 is what the torsional stiffness is proportional to, and to a large extent your transverse shear can also be handled better with that. So it's a combination of the transverse shear due to the shear forces and the transverse shear stresses which are coming because of the torque as well, which elements of this box beam skin, both the spar as well as the cover skin, are expected to handle. So you try to push them as far out as possible. Of course, the collateral benefit that you get out of this is that you have a greater volume within which you can enclose fuel, you can enclose all the cables going to power various things like let's say the actuators for the control surfaces, etc. So all of these have to be enclosed within the wing. So essentially you get more room for keeping all those things as well. So arranging those within that volume. So then basically the design would be appropriate. This alone would be appropriate if the load is directly applied as the global torque and the bending moment mx, like what we considered as examples 3a, for example, where we had just a tip moment in a cantilever, or 3b, in which we considered a couple of weeks back the example where there's a tip load on a cantilever. But we know that that's not how the actual loading on the aircraft is. It could be probably the simplest example that you could have is an elliptical loading, but then you would have a shrinks approximation based on the planform area changing as well over the span, and that has to be accounted for as well, the sweep, etc. Many other complications are there. So you typically do not have a tip load. First of all, you have a distributed load, whether it is the lift or the drag, and in addition you have the concentrated loads coming from the self weight of the wing and whatever is occupying the wing, like the fuel and the control surfaces and the etc., the actuators, etc., and then the engine and its weight and thrust as well. So this being the situation, we have to go for looking at actually how the load is getting transferred. It is not a tip moment or a tip force that has to be transferred, but this distributed air loads, like what is shown in this particular picture over here. You see some kind of a distribution is drawn both on the positive and the negative sides. So usually, of course, you have the suction on the top and the pressure on the bottom, relatively speaking, which is why that differential is what causes the lift distribution that is there. But essentially, those are aerodynamic loads and they are distributed. And if it's a low Reynolds number aircraft, that is a lower speed and or smaller aircraft, then the shear loads in the boundary layer become important as well. But again, they are much smaller compared to the pressure distributions. So at least we have to be able to take care of these pressure distributions or suction on the bottom side, the top side. So on the cover skin of the wing. And of course the fuselage as well. And in addition, as we talked about, there are many examples of the concentrated loads. In the case of the fuselage, it could be coming from the landing gear if it's a nose gear kind of configuration. The other two landing gears sometimes could be on the wing as well. So you have the loads coming on the wing as well. So again, depends on the landing gear designs as well. So essentially what is happening is that there is a distributed load, but that distribution is on the cover skin. So the cover skin, what it does is, since it is very thin, it cannot take all of that load. So it has to very quickly transfer this load to a much more capable structural element, which the nearest element happens to be a stringer. So if we take a small panel over here, so let's say take a small panel over here. So it's let's say between two stringers. So there is one stringer on the left and one stringer on the right, and there is a certain amount of aerodynamic load which is acting on that panel. So if those stringers were not there, the panel would not be able to handle that. So what it basically does is that though the load itself is acting on the cover skin, eventually it transfers that load to the stringer, so to both the adjacent stringers that are there, so that it acts basically as a panel rather than the whole. It's not the entire element on the top, which is one panel like that. So even though from a structural point of view or a manufacturing point of view, you have made it as a single entity, because of the presence of these stiffening elements, it's a much smaller panel than that, and which is actually quite beneficial to have. So the loads are collected locally, the pressure loads, so whether it's on the top or the bottom, and then they are transferred. So this transfer of load is what we refer to as load transfer as a topic, very important topic in structural analysis. And it is basically to the major load carrying members, in this case the stringer. So an improper design, what it would do is that the loads would produce excessive local deformation. So in other words, if you have, let's say you don't have this particular stringer, this stringer was not there, then the distance between this stringer and the next one becomes very large, and therefore this particular part of the skin might deform like this, which means that of course here we have shown just the box beam, but if it's the airfoil, then you are basically having a very large change in the airfoil shape itself, and the aerodynamic characteristics can be greatly affected. So this placement of stringers is very, very critical. So you have to place it close enough so that the deformations are not large enough to change the aerodynamic characteristics beyond a certain level, and at the same time it cannot be so close that you have too many stringers and therefore you have a weight penalty coming because of them. So it's always a trade-off. All design decisions like this are trade-offs, and sometimes the conflicting requirements can come from different aspects. So as in this case, one is an aerodynamic aspect where you want the stringers close by, and the structural aspect or the weight aspect from which you want it farther away. So you have to have a trade-off between that and find out the optimal distance or the pitch between the stringers. So the loads, if it was an improper design, that is the stringer spacing is very large, it would have excessive local deflections, and that's what we said is not permissible in an aerodynamic sense. So now if you look at the load transfer path, we already discussed that there is an airflow over the wing, and that would be very similar to what it is over the tail, and as the fuselage is very different as well, just that it does not generate lift or as much lift as the wing, and neither does the tail. So they generate much smaller amounts of lift, fractions of lift compared to the overall lift that is generated by the aircraft, most of it being generated by the wing. So that airflow is having a certain pressure distribution, and that pressure distribution essentially is acting on the skin, whether it is the wing skin or the fuselage skin or the tail skin. It is basically acting directly on the skin, but eventually the skin is getting transferred to the next nearest stringer or a longeron. As we discussed in an earlier class, the stringer and longeron are essentially performing the same function, but the longerons are much longer. They do not have cuts in them because of the occurrence of something in between, like in the case of a fuselage it could be a window, or in the case of wing it could be the a particular portion of the rib which cannot be cut off. Whereas most stringers will pass through the through cutouts in the ribs, some may not, and then you have what we typically call as a stringer, but these are interchangeably used and have different connotations in different parts of the aircraft industry. So essentially the transfer is happening from the air to the skin, and from the skin to the stringer, and it doesn't stop there. From the stringer it goes to the transfer stiffening elements, which could be, in the case of the wing, the ribs. In the case of the fuselage, it would be either the frame, which is a much lighter construction, hollow, whereas bulkhead, which could be typically, let's say, at the front and the rear, you could have a bulkhead. And similarly, where the wing is attached, also the frames would be much heavier, because the load that is coming from the wing to the fuselage is very large over there. Essentially, you can think of the wing as a cantilever beam, that is a free end and a fixed end. And in that sense, is there a possibility of considering the fuselage as a beam? Anybody? Any thoughts on that? If we are modeling, let's say, the wing, the horizontal tail and the vertical tail all as cantilever beams, one end is fixed to the fuselage, of course, and the other end is free. On that you have a distributed load. So that is the first cut analysis. To any preliminary analysis will start like that, to treat these aerodynamic surfaces as cantilever beams. So in that sense, what would you treat the fuselage as?
So during pitching, it can be called as cantilever beam if the tails are considered.
Okay.
Am I wrong?
Yeah. Let's listen a few more inputs, and then I'll tell you.
Okay.
Yeah.
Okay, sir.
Yeah. Anybody else? Come again?
Free beam, sir.
Free beam. Okay. Good perspective. Yes. What else?
Sir, it's so if the
One at a time. Yeah. Tell me, Samanvai.
okay, sir, it can be treated simply supported also.
Yeah. So in what way is it simply supported? So simply supported means it has to have two hinge kind of supports, one which is fixed, the other which is on rollers. So what are you talking about as far as the fuselage are concerned? What are those two supports?
Sir, two hinges, like front wings and the back wings.
Yeah.
Tail.
Okay. So that's more like it. That's a better approximation. Of course, all of these approximations are going to be kind of crude, but what we are talking about is a preliminary design. So this is good enough to get ballpark values. So from that perspective, what Samanvai said is appropriate, that you treat the wing as one of the hinges on which the simply supported beam is getting supported, and the other is the horizontal horizontal tail. And of course, it's not a regular kind of a simply supported beam that the hinges are at the ends. There is going to be an overhang because the wing is at a different location over here. So in other words, if we draw the simply supported beam, what we are talking about is basically, let's say, a hinge over here, and then on rollers you have at the tail over here. So this becomes the tail, and this becomes your wing, and this is your fuselage. So as a first cut analysis, we typically deal with this. So many people think that the simply supported beam hardly has any examples as far as aircraft is concerned. But very interestingly, the first cut analysis for the fuselage is a overhang, as a simply supported beam with an overhang. So that is a good point that Samanvay brought about. So that is sometimes considered, but as I said, all of these approximations are a little crude, so we eventually need to go into better approximations. So coming back to the load transfer, you have the stringers which are transmitting that load to the next available rib. In this case, for example, if it's along the length over here, the next available rib over here, rib at this particular location.
Meanwhile, while Professor joins you, I have some suggestions regarding assignments. Some people have written assignments just one page, and like some people have written only half a page without having any information, like full of negligence. And some people wrote assignments like a book. Some person wrote 23 pages, assignment 5. Full 23 pages. So there is no point in writing 25 pages, 100 pages unless you are not writing. If there is no relatable content, we don't hesitate to put 0 marks. Okay. So please take note of this. Don't write 100 like 20-30 pages for where you need only 4-5 pages. So is it audible to everyone?
Yes.
Yeah. So, and while you're taking what you call screenshot or scanning, use some good scanning apps like what you have, PDF Lens or some other good apps, so that the clarity will be good. So some assignments it's very difficult to read. Okay, so please take note of this. Thank you.
Okay, thank you, Rajesh. So continuing, so from the skin it goes to the stringer, and from the stringer to the rib, and then from the ribs to the spars. So as far as the fuselage is concerned, the equivalent path is from this fuselage skin to the stringers or longerons, and then to the frames or bulkheads, and then eventually to the floor beams, which are equivalent of the spars on the wings or the tail. So this is the path through which the flow happens, and eventually these two beams are sets of beams are connected. That is, on the one hand you have cantilever beams from the aerodynamic surfaces, and then you have the simply supported beams. So when you are treating the cantilevers, you are treating the fuselage as a rigid support for those cantilevers, and when you are dealing with the fuselage design, preliminary design structurally, you are treating the fuselage as basically a simply supported beam with a overhang, which is on the which is having the aerodynamic surfaces as its hinges. So so you're not treating all of these as beam elements at the same time. If you do, then what the other person answered actually is very correct. That is a free beam. So you have a set of free beams which are all interconnected. Overall condition is that it's free, but then it's all interconnected between them. So if you want to analyze the overall behavior of the entire aircraft. So now the air pressure distribution on the outer surfaces of the beam is going to be causing those bending loads. and predominantly, of course, the transverse shear is one of the collateral effects, but as we saw, the maximum transverse shear stress is much smaller compared to the maximum bending stresses. Yes, the maximum transverse shear stresses will also get additional values from the torsion because of the pitching moment and or the other concentrated forces being not aligned with the CG. Therefore, you would have a few other torques causing the transverse shear as well. But in spite of all of that, the maximum transverse shear stress that you have anywhere on the aircraft will be much smaller compared to the bending stresses. The bending loads are the dominant ones, and within the bending loads, again, the bending load due to the lift distribution is what is far more dominant, as we saw in the when I was explaining about moving the engine from the wing to the fuselage not being an issue. We saw that the other things are very, very small fractions, whether it's from the drag, the thrust, the self weight of the wing, because the lift of the wing is pretty much balancing the entire aircraft's weight, whereas the weight of the wing alone will be much smaller fraction of that. So the self weight of the wing will be a very small compensating factor compared to that. So then similarly, whether it's the thrust of the engine, the thrust to weight ratio of the engine is improving continuously with the propulsion technologies that we have today, and therefore that's fairly large as well, and therefore the weight of the engine again is not a major load that you are having over there. In any case, it's a compensating load, but it's a small compensating load. So the bending loads are the dominant ones, and coming from the air pressure distribution, and the skin's bending stiffness is too low to resist that air pressure by itself. If it were, for example, a monocoque construction, it should have a very thick skin if at all it is able to resist that, which is why the weight penalty will become so much that the larger, faster aircraft should go for a semi-monocoque construction. So to avoid these large deflections within the skin is why we have introduced these longitudinal stringers which pick up all of these air loads so that they can then transmit it to something else. So these stiffeners are usually slender axial members. In this case, for example, you see just a T kind of a section in the top right corner, and it could be an I section, it could be sometimes a channel section, it could be a Z section, whatever. In other words, they themselves are having moderate bending stiffness, but remember that the bending load is not acting on this, it's actually acting on the entire box beam. So the stringers by themselves are actually acting like axial rods. So in other words, some of them are entirely in tension, or some of them are entirely in compression. So they are not suffering bending, as so to speak. They are suffering only axial loads. So therefore, their moderate bending stiffness is not of a concern. It's the bending stiffness of the entire box beam that is of interest to us. Okay, so now the transverse loads are picked up by the stiffeners to be transferred quickly to the more rigid ribs, which again, just like the stringer spacing is an important design parameter, the rib spacing is going to be an important design parameter as well. Obviously, you're going to have, where the concentrated loads are there, you definitely will have large thickness ribs. That is, for example, where the fuselage and the wing are connected to each other, or the horizontal tail and the vertical tail are connected to the fuselage. Those places will have very large, in the case of the fuselage, the frames, and in the case of the aerodynamic surfaces, the ribs. Similarly, where the engine is attached, you will have a rib or a couple of ribs around that location. Similarly, where the shift is taking place between the flap and the aileron, you might have a rib over there. So apart from these obvious locations, between them again there will be certain lighter ribs, much thinner compared to these ribs that I already talked about, but that's what ensures that the skin panel is sufficiently small in size, just like it is small in size along the chord direction because of the placement of the stringers. Along the span direction also, the panel size of the cover skin is shortened by the appropriate placement of the ribs. So if you have many ribs placed close by, you are having much smaller panel in the span-wise direction as well, which can delay, for example, the buckling of the top wing surface. So essentially we're talking about the load transfer over here. We came all the way up to the skin transferring it to the stringer, and the stringer transferring it to the ribs. So next what happens is what we will see: the ribs collect all of these transverse loads from the stiffeners. See, one is the possibility of buckling of the cover skin, but also the top stringers can also undergo buckling because they are under compressive load. So they are not under bending load, but they are under compressive load because of the bending load. So that can cause their buckling unless the ribs are appropriately placed. And again, you have a problem of plenty. If you have too many ribs, the weight penalty is going to be there. So again, just like the decision on the stringer is a trade-off between the aerodynamic and structural consideration or weight consideration, same thing happens with the rib as well. So the ribs will collect all these transverse loads which are coming from the stiffeners, and then they have to transfer it in turn. So it's basically a passing game that is happening over here, and that they have to transfer it to the largest structural element that you have there, which is nothing but your spar. And in general you will have multiple spars, and here you see an example where you have a front spar and a rear spar in a single box beam. So this transfer to the wide flange beams, we call it wide flange because you see that the flanges, that is the spar caps, are fairly large in cross-sectional area compared to the stringers. The stringer cross-sectional area is very small for each stringer, but of course if you put all the stringers together, they are quite substantial as well, but each stringer is fairly small, and that's what is collecting the air load from the skin before transferring it to the rib, and the rib to the spar. So the wide flange beam or the spar is designed to take that transverse shear load through the spar web that you have on both the sides, in addition to the cover skin, because the cover skin, remember, is taking the transverse shear due to the torque and the drag, which is very small. The drag is very small, but whereas the lift is what is the predominant thing, and so this element that is basically the spar web becomes a very, very critical member, because the transverse shear stress is to be taken by that. The dominant transverse shear stress, which is coming from the lift distribution, has to be taken by those spar webs, how many ever they are, depending upon the number of spars. So therefore, now we see that this entire from the air all the way to the largest structural element you have, that load path is basically completed. It doesn't mean that these in-between things are not stressed. They're all obviously stressed and undergo certain deflections, but they are supported elsewhere, and they are basically transferring that load to a more capable structure, and that eventually ends up with the spar or the floor beam. In terms of a load path that we are talking about. And then of course you talk about the overall connections that are there, and eventually how that load creates a particular kind of motion for the aircraft in terms of the inertial load, and therefore how the aircraft either is in a steady state of motion if the force equilibrium is there, or if there is a force or moment non-equilibrium there, mismatch. Therefore you would have an acceleration in those respective directions, either translational accelerations of an aircraft accelerating in its forward direction or vertical direction, or it could be a rotational motion which is ensuing because of unbalanced moment that is there coming for a short duration, in order to perform certain maneuvers and change of attitude or change of the particular part of the flight mission path. So besides serving as the local load distributors, these stiffeners, that is the stringers that we are talking about over here, are going to also contribute towards the box beam's bending capability as a whole. It's not only the spar caps that are going to be causing the capability of taking the bending load, but also the stringers. They are going to be contributing as well in an indirect fashion, because they are basically taking the tensile and the compressive loads. So now we look at the wing or tail, which are the aerodynamic surfaces on the one hand and the fuselage structures on the other hand. The skeletal construction looks like what you see on the right hand side, which shows the central upper fuselage assembly with the skin removed. It's just the transverse stiffeners, which are your frames. So this is an example of a frame, whereas this is an example of a stringer or a longeron. So the wing and the fuselage are the two major airframe components, and the horizontal and vertical stabilizers, as I said earlier. The structural behavior is going to resemble the wing, and therefore qualitatively we have understood how to handle the wing, we know how to handle the tail as well. So the wing and the fuselage typically exemplify the structural mechanics principles employed in entire flight vehicle structures, and within them also they have a lot of parallels, as we discussed in the previous slide. So then if you look at the wing structure, again here you're talking of a typical wing spar construction schematic, of which is shown over here, and that spar has certain vertical stiffeners that are coming in between. It could be a part of a rib, for example, and then you have the caps and the webs which are running along the span of the wing. So the main function of the wing structure as a whole, typically made out of either a single or multiple box beams, is to pick up the air and the engine loads and then transmit it to the fuselage. So the wing cross section that you have is obviously from the aerodynamic consideration airfoil, which is designed based on what is the lift required, what is the L by D ratio required, based on the aspect ratio, the sweep, the dihedral, the wash in, wash out, etc. So various factors come in over there. But from the structural point of view, we are seeing it as a combination of four parts, namely the ribs, the axial members, which are the stringers, some taking compression, some taking the tension, and then you have the bending members, which are the spars predominantly, the bending load predominantly, the normal loads taken by the caps, and then the transverse shear loads taken by their webs, along with the cover skin. But the cover skin's role is kind of limited because the lift distribution is usually for most flight faces perpendicular to that, and therefore it's not taking much of the transverse shear due to the lift under most situations. So then coming to the spar, as you know, it's a heavy span-wise beam, typically kind of an I section, as you see in this particular example, and then it takes the transverse shear load through its web, and then the span-wise bending through its caps. So the spar is basically made out of two parts, as you know, the thin shear panel or the web that you see over here, and then the heavy caps that you see at the top and the bottom, which are basically taking the bending, one under compression, the other under tension. So continuing this, now let's look at the rib, the typical wing rib construction. So at various locations along the span you have this. These ribs are basically planar chordwise structures. So in other words, they are present parallel to the chord direction. So at various locations along the span, parallel to the chord. And these planar structures are therefore taking the in-plane loads that are coming, which are being transmitted from the stringer and then transferred to the spars. So they redistribute the loads, as we already saw. So the ribs are holding the skin and the stringer to their designed contour shape, so that the airfoil configuration is kind of maintained to a reasonable extent. Yes, there is a small change because of the deformations that are happening, but essentially it doesn't modify the aerodynamic characteristics a whole bit. So that is your skin stringer designed to the contour shape, and then you have very large skin stringer compressive load capability because of this that you need to have to hold the skin stringer to the designed contour shape, means that the skin stringer has to have a very large compressive load capability, especially on the top surface that we are talking about, because of the very large lift distribution, especially at the values of N1 or with the Gust modifying the flight envelope, and N4, which could be larger than the N1. So at those kinds of configurations, the skin stringers on the top will be really tested. So we will see in terms of the material choices also how that makes a big difference. And of course they are supported by the span-wise spars in this particular task. That is what the ribs see. You can see at the front of the rib and the rear of the rib, it's kind of supported by the front spar and the rear spar. So then continuing with the wing structure, the cover skin along with the spar webs essentially forms a efficient torsion member, because it's a thin walled closed cross section that you have. In larger aircraft it would be a multi cell kind of a configuration. So the subsonic aircraft's thin wing skin may be designed to undergo post buckling. So in Airbus A350 like this, or an Airbus A320 that you see over here, very typical kind of transport kind of an aircraft, which are not subsonic, transonic, close to Mach 0.8 or a little more than that. So under that situation, what you're essentially seeing is that you are capable of taking those bending loads, and these bending loads causing compression on the top surface. The stringer should not buckle on the top, but the skin can be allowed to buckle, and operates in the post buckling regime. So which makes that the thin skin makes the contribution to the wing box bending quite negligible, because if it has already buckled, then obviously it's no longer able to take the compressive load. All of that compressive load, which was shared between the skin and the stringers on the top, is now taken only by the stringers on the top. So that kind of a situation means that the bending, the stringers have to be designed for such kind of an eventuality, which is not actually an eventuality, which might be a very common situation in regular flight itself. So the thin skin makes a negligible contribution to the wing box bending, which implies that the bending moment is almost entirely taken by the spars and the stringers, which is what has to be the design kind of a situation for them. Now we'll look at these two configurations that we have. One where you do not have any stringers, which you see on the right hand side over here, and one in which you do have stringers, which you see on the left hand side over here, both having two spars. And the cover skin a very similar airfoil configuration, but seeing what is the essential difference between having stringers and not having stringers. So the two types of wing cross section that you have here are both for subsonic kind of an aircraft with two spars, and one is basically what we call as the concentrated flange type. That is what you see over here, which consists only of spars. To take the front spar and the rear spar, to take all of the bending, which is essentially coming from the lift distribution, also from the small amount from the drag distribution. But the other example that you see on the left hand side over here, which is the more common one, especially as the sizes increase or the speeds increase, is where you have a distributed flange type. So in other words, you do not have a single or just two flanges, but you have multiple flanges. In other words, the flange gets split. So you have the flange for the spar, and then you have connected through the skin the stringers, which are also acting as additional kind of spar caps in terms of functionality. So it's a distributed flange type is what we call. So instead of one wide flange, you have a distributed set of flanges coming from the stringers. So which uses both the spar caps as well as the stringers in order to take the overall bending. The skin, of course, already has buckled on the top and is not taking, but the bottom skin will continue to offer some bit of resistance to the tension coming because of the bending. Okay, now I'll stop with this particular slide where in the previous slide we talked about a subsonic aircraft. Here we are talking of a supersonic aircraft, which is much thinner airfoil cross sections that we deal with. So for example, what you see over here, which is within a red rectangle, highlighted within a red rectangle, you see much thinner cross sections. In other words, the thickness to chord ratio, that is, this is the chord direction. So your T by C in the case of supersonic aircraft will be much smaller compared to the same thing for subsonic aircraft. Okay, so that being the case, but of course the load is going to be very large. So not only you have the regular loads coming because of the larger dynamic pressure that you have because the V has exceeded the speed of sound. In addition, you are going to have in the other direction the wave drag. So that's going to contribute a larger amount of drag as well. So essentially at larger speeds you are going to encounter larger loads. So which means that if you do not have anything else, you need to have thicker skins, and because you have first of all a thinner airfoil from the aerodynamic consideration, so you need to go for a thicker airfoil over there. You're probably not seeing my slide, or are you? Are you seeing my slide?
Yes, sir, we can.
Okay. Fine. So the supersonic airfoil is a thinner compared to the subsonic, and therefore you need to have a thicker skin in order to handle the load. Even if the load had not increased, just because you have a thinner airfoil, you should have a thicker skin. So you have a thinner airfoil overall. That is, the overall thickness is smaller, but the thickness of the skin within that, in other words, the amount of empty space that you have in between the hollow wing is going to reduce. So that's basically what we are talking of, a thicker skin over here in a thinner airfoil. So because in addition, if it was the same load also it would have happened, but now it's a larger load because you're going to withstand even larger surface air loads. So from both the perspective of a larger load and a thinner airfoil, you need a thicker skin. So both of these are adding to the requirement of the skin thickness, which means that you're going to have an increase in the wing box capability. You need to build up, as far as your structural design is concerned, you should have a wing box which is even more higher bending capability than what you designed for the subsonic aircraft. So the stiffeners typically in such situations, because it's very thin, are manufactured as integral parts of the skin. So if it's a metallic structure, then it would be manufactured using forging or machining. And if it's, let's say, a composite kind of aircraft, supersonic aircraft wing, then you would have co-curing of the wing skin along with the stringers and the spar caps or spar webs. So all of these are made as a single unit is what it means. So that's what is the integral parts, and these are of course the subtractive ways of manufacturing. Slowly we're moving towards additive manufacturing, though in terms of the mechanical properties we have not yet reached a stage where we can replicate the subtractive manufacturing, but in many situations of additive manufacturing or 3D printing as it is more popularly called, we are approaching that values closer to that. So in that, essentially you are having an integral manufacture there, because you're not manufacturing it in a subtractive way. So I think with this slide probably I will stop today's class. There might be a few concluding remarks on the load transfer in the next class before we revisit the materials that we have seen earlier, especially the metallic materials, to see where we stand in terms of, now that we know the purpose of each one of these components, like the spar cap, spar web, the stringers, the cover skin, etc., which material suits which particular component would be kind of more easy or logical to reach out, and therefore those kinds of qualitative statements we will make by revisiting some of those materials. And once we are done with that, we will take a detour and look at some basic aspects of the theory of elasticity. So in the next class we will revisit the materials, and then in the next week onwards, I think to almost the end of the course, we will be looking at those aspects of elasticity which are going to stay with us. I'm actually not going to cover a lot of the torsion formulae and the bending formulae, because many of them are kind of outdated and are no longer actually used in the regular aircraft industry, even for preliminary design. So there are much better methodologies, both using finite element analysis in a numerical sense, as well as even analytical techniques have drastically improved. So many of these things, if you learn also, you're not going to actually use in an aircraft industry. So I'll be skipping many of those, but giving you those essential terminology which you need to know in order to understand when somebody talks about a structural design or a structural analysis or even a failure analysis, what are the things that you need to be aware of. So these are the aspects that we will cover from the next week onwards. Things whose definitions and whose relationships do not change even with higher fidelity models, which are much more accurate and at the same time computationally efficient as well. So it's towards catering those more realistic requirements that our course will be focused on, which is why I gave a lot of homeworks earlier on related to those simpler formula towards bending and towards torsion, so that you understand when we look at more complex ways of handling this state-of-the-art methodologies, you would see where those formulas stand in terms of just giving you ballpark values, but of not much significance in terms of takeaway, especially in an aircraft company like situation. So with this, I complete today's class. If anybody has any questions, please let me know.
Hello, sir.
Yes, Samandar.
Sir, talking about the homeworks, in one of the homeworks you have given, we were having ellipse cross section, and in that we had to find the sigma max and the tau max values. So you said in theory of elasticity many equations are outdated. So we'll be dealing with analytical approach also.
Yeah.
So are there different analytical approaches in which this aerofoil cross section can be dealt with? Because while doing it for ellipse cross sections, we need to do some of the derivations.
Correct.
Because that were not given in the book. So are these available for this aerofoil cross sections?
Yeah. So for airfoil cross sections, as you know, there are many different airfoil cross sections. Even if you take just the subsonic regime, there are many different airfoil configurations. So it's kind of very difficult to arrive at closed form analytical solutions for them. So you would typically go for a finite element analysis, but you will not go for a 3D finite element analysis, which used to be the case for about 10 to 20 years back. Almost everything was done using 3D finite element analysis, and that used to be computationally so intensive that to analyze the wing as a whole, you typically take a few months. That's pretty much a crime, because there are numerical techniques which can break this 3D problem into two parts, 2D and 1D, which is why I showed you in I think the previous class the airfoil cross section of a helicopter rotor blade, where we had a finite element discretization of the graphite epoxy, glass epoxy, steel, etc. that were and foam that was part of that particular configuration. So that's what you would do to a 2D analysis of that cross section in order to arrive at that entire matrix of 4x4 stiffness matrix, which involves extension, bend, the two bending and torsion. So all of those stiffnesses and their couplings, the couplings between them, and the nonlinearity, which means that you may not have constants within that matrix. So all of that can actually be done. There are software which exists in order to accomplish that. but it's kind of beyond the scope of this particular course. So as far as the homeworks are concerned, I expect you to use the simplest kind of formula that are available, or approximations that are available. But it's a good question that you brought out, that in reality you have a cross section which is even more complicated than the ellipse, and therefore you would not be dealing with it using these closed form analytical methodologies. But if you break up the wing, not analyzing it as an airfoil entirely, but you're analyzing it as a combination of many wing panels, each of which is a plate, and then the stringers, each of which is like a rod, and the spar, which is like a beam, or multiple spars or multiple beams. So then you're treating each of them individually as elements. Then you can have closed form analytical solutions also for each one of those elements, and there are ways of putting all of these together by including the appropriate boundary conditions, or rather the contact forces or contact stresses that are going to arise depending upon the kind of joints that you're going to have, either an integral manufacture or an adhesive bond or a rivet or a bolt. All of these can be eventually analyzed. Is that clear, Samanvay?
Thank you, sir.
Yeah,
Yes,
you're welcome.
thank you, sir.
Yeah. Anybody else? Any questions? Okay, thank you very much then. We'll catch up on Thursday. Take care. Bye-bye.
Bye, sir. Thank you.
Bye-bye.
Thank you, sir.
Welcome.
Thank you, sir.
Most welcome.
Thank you, sir.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् ये ते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा